Okay, for 12.7b, we're actually going to do like a little lesson on a technique that has been showing up the last couple of years on the AP test. So get a blank piece of paper. You can pause the video for a second and grab a blank piece of paper. And so this is going to be 12.7b. There's going to be a worksheet that goes with it. And so this is going to be, the title is definite integral. So definite integral we have a lot of experience with, right? As the limit, we've done a lot of stuff with limits of a Riemann sum. And I think we have had a lot of experience with Riemann sums, which are areas on our curve with rectangles. So this is just combining a few things that we've done a lot of stuff with. It's going to be a little weird at first, but I think once you get the hang of it, it won't be a problem. But if I never showed you guys this, you'd have no clue on it. First of all, before we start with this, let's talk about a couple things that you should understand that maybe you've seen in previous math classes. So there's something called sigma notation, and that's a Greek letter, sigma. And I'll just show you an example of how we use it. You can say k equals 1 to 5. And then there's some sort of like formula involving k in here. And so k is like a counter, so the first term we plug 1 in, and the second term we plug 2 in, and the third term we plug 3 in. So sigma notation, this is used to represent accumulation like integrals. So it's going to make sense, I guess, to tie this to integrals. And this is the formula. You're plugging integers only for k, and then you're adding them up. So, we could keep going, and we would stop at the number at the top, and then we would add these all up. So this is 1 plus 4 plus 9 plus 16 plus 25. So it's 14, 30, 55 would be the answer. Okay. Now, that's not calculus on its own. We use these in series, and that's a big topic in BC, but it's something that could come up as early as Algebra 1. A sequence is a list of numbers, a list, so there's commas in between them. And there's usually a pattern. A series is what we just found. It's the sum of a sequence. So it's all the terms in a sequence added up. We call those terms. Now, this is sort of a BC topic. We're not going to actually do series or sequences right now, but we're going to use the notation that is often used with these. We're going to use the sigma notation to add a bunch of things up. So here we go. There's a little introduction to some of the tools we're going to use. Now, we've been taking, we've been approximating integrals with Riemann sums. So let's talk about that real quick. So let's just make some generic graph, and we're going to say slice it up. Okay, we'll do 4 equal slices. Now, the problems that we do don't always have equal width slices, but on today's problems, they will always be equal. Okay, in this case, they're all ones. Now, the height, we're going to create rectangles here. We could do left end, right end, midpoint. We could do trapezoids. So we're going to go ahead and start with left end point, Riemann sum. That means you use the height on the left side. And so the value here would be f of 2. This would be f of 3. So this function, this is the function f of x. And so we could plug in the x coordinates here to get the y coordinates, which are going to give you the height of each slice. And we're not going to use f6. like in a table, sometimes, if we could do right in instead, that would be different. And so what we're going to do is we're going to use these rectangles. We're going to find the area of them, and we're going to say, well, that's roughly the area under this curve. And we usually use it when they give us a table of values because we don't have the function of the curve. Now, in this case, let's say that we said we have 4 slices, and they're going to have equal width, which for our rectangles equals the base, right? And let's say that we didn't know what the bases were going to be. We could figure it out by saying, one way that we could calculate it is we could take the difference between the top and the bottom and divide it by the number of slices, and that would give us the equal width of each slice. So we could do upper limit minus lower limit divided by the number of slices. Now I'm writing this all because this is going to help us ease into something new. So in this case, it'd be 6 minus 2 over 4, which would be 4 over 4, which would give you 1. Because we're not going to want to always draw these pictures. But drawing the pictures kind of helps us understand our strategy. Now, a lot of times this base we might call dx, right? Like the width of the slice, or delta x with a triangle, which is actually a Greek letter delta, which represents a small change in things. So we got that. Now, if we wanted to use this to estimate the integral of f of x from 2 to 6, so all the way 2 to 6, and this is something you guys had to do in your last practice test, now I'm using kind of some generic terms here. I don't actually have y values, so I'm going to say, all right, we're going to do f of 2 times 1 plus f of 3 times 1 plus f of 4 times 1 plus f of 5 times 1. We're doing rectangles. Base times height times base. Now, this is where we're going to try and bring in this sigma notation. What I want to do is say, okay, it's kind of like we have a pattern here, right? And so another way to write this is to say, okay, let's use this sigma notation. Start at k equals 1 and end at 4. Okay? Now, k equals 1 is usually for the first slice. Okay? Sometimes we start at k equals 0, which my computer science students should appreciate. But a lot of times k equals 1 is kind of a nice place to start. K equals 1, k equals 2, k equals 3, k equals 4, right? First term, second term, third term, fourth term, first slice, second slice, third slice, fourth slice. And then we can use the k value to help us figure out what the formula is. So in general, it looks like it's always k plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. So I think it's going to be f of k plus 1 times the base, which are always the same. And this is going to be our delta x or our dx, which we're going to figure out with that strategy up there. Now, what we've done is we've rewritten this definite integral as this estimation for a definite integral as a in sigma notation as the sum of some terms of a sequence. So that's kind of a new thing that we could maybe represent it in a different way. We'd call this like the open form and this the closed form. They both represent the same thing, but this is like the compact version of it. Now, here's the deal. That's approximation. What I want to get into today is getting the exact answer using this approach. Now, to find the exact answer, and this is an idea that we've been talking about for a long time, we could just do more slices, make them thinner, and it'll get better. And if we make them infinitely thin and infinitely many slices between 2 and 6, it will approach the correct answer. So I'm going to say infinite slices that are infinitely thin. right? I mean, that's not a new idea. That's kind of how we figure out the definition of the derivative and or integrals. But I want to figure out how we could write this as like in this kind of form here. So I'm going to go ahead and kind of draw my generic curve again, my f of x curve, and we're going to go from 2 to 6 again. But we're not going to do 4 slices. We're going to do infinite slices. So, and just to represent it, like this is f of 2, this is f of 6, just like before, but we're going to do these really thin slices. Now, they're going to be so thin that you wouldn't be able to see them because they're going to be infinitely thin, but we're going to draw them so we can actually tell. So we have these thin slices, and we're going to add them all up. And so let's go to the middle here to some generic slice in the middle of it at some x coordinate between 2 and 6. It has a y value of f of x, right? The thickness of the slice is now what we usually refer to as dx, or delta x is a common way of referring to it in these kind of problems. So, let's see. Now, here's the now the area of this kind of general slice. There's going to be a bunch of slices, right? The area of that slice equals the height of the slice, fx, times the thickness of the slice, dx, or delta x. The challenge is, well, if we're going to talk about, this is what I'm going to say. Let's say that this is the kth slice, because I want to be able to write a formula involving like number of slices. How many slices have we done? First slice, second slice, third slice. So on the kth slice, how do we come up with an expression? Like for instance, if this was the 50th slice, what would that area look like? And the first thing you'd want to do is you'd say, well, on the 50th slice, what x coordinate are we at? Right? What x coordinate are we at? And the x coordinate is going to be where we started plus the 50 slices times their thickness. They're all going to have equal thickness. So to get to that x coordinate there of the kth slice, the x coordinate is going to be where we started plus how many slices we've done times the thickness of the slices will give you that x coordinate, right? So that's kind of an idea that we need to understand. So the x is always going to be the lower limit. This is the lower limit, right? Plus how many slices, k, times the thickness of each slice, delta x. So this is how we find where we're at, okay? So if we come up here, we could say, all right, well, 2 to 6 of f of x dx is exactly, and we're going to use this sigma notation, leave some room in front of it. Up here, we were doing approximation. Now I want to do exactly. We're going to start at k equals 1, and we're going to go to infinity. Now, instead of writing infinity here, that's a little not like, not the best, most perfect way to write it. Instead, we do this. We say limit as n goes to infinity, and then we put an in there. All right? Instead, that's a little more proper. And we say, well, we want the height of each slice, which is going to be whatever the x coordinate is that we just figured out plugged into the function. So it's going to be f of 2, the lower limit, plus k times the thickness of the slices. Now, the thickness of the slices, we're going to figure out the same way we just did up here when we said we wanted 4 slices. This is how we figured it out. Top minus bottom divided by number of slices. There you go. Same idea here, but we're going to have infinite slices. So delta x, the thickness of the slices, is still going to be the upper limit minus the lower limit divided by the number of slices. Same exact thing I wrote up above. But this time, and the upper limit and the lower limit are still 6 minus 2. The number of slices, though, is in. Because we're going to go to infinity, but instead of putting infinity, we put in. And so that's going to give us 4 over n, which is your delta x. And that's what's going to go in here, because we said that the x coordinate is the lower limit, 2, plus k times delta x. Well, we're going to put 4 over n here. Our goal here is to write this without any x's in it. Then, to get that, that's the height of the slice. You need the width of the slice to get the area of one rectangle. And so you're going to multiply by another 4 over n. And this n is going to equal the number of slices. But this is the way we write, and we're going to do several examples so you get the hang of it. This is something that I think if you just practice, you can get pretty good at. Excuse me. Okay. So in general, so that was kind of a little more to the specific problem. In general, if you want to integrate from a to b of some function fx dx, it's going to equal the limit as n goes to infinity of sigma k equals 1 to n. It's going to be the height at x times delta x. Right? So that's your general approach. The hard part is that x is going to equal the lower limit, in this case a, plus k times delta x, right? And delta x is going to equal the upper limit minus the lower limit divided by the number of terms, which also means that x over here can be written as a plus k times b minus a over n. So we need those to help us. So that's the idea, because what we're doing here is it's like we're doing a bunch of slices like Reimann sums, right? But we're going to take them to infinity. So this is one way of sort of defining an integral. This is like the definition of an integral. We kind of, I guess, have avoided it so far, but you might get like one question, multiple choice or something on your AP test that might have this on it. Let's try some examples. So still on your own piece of paper, and then I'm going to give you guys an assignment. We might write a few things on it before you work on it on yourself. So let's try a few examples. And there's going to be kind of two different ways that you might be given problems with this. One way you might be doing like we're doing right now, taking an integral and writing it as a limit of a Reimann sum, but you might be given the limit of a Reimann sum and need to realize that you're trying to find an integral. So let's try this. 5 to 7 of x to the 4th dx. So we're going to put some real functions in there, okay? It's going to equal the limit as n, the number of slices, goes to infinity of the summation of k equals 1 to n. So that's the same every single time we do this. What we need to figure out is okay, well, we want to, instead of putting fx here, we actually have a function. The function is x to the 4th. But we need to plug in the right expression for x that doesn't have x's in it. So we said, okay, well, that's the lower limit plus the number of slices k, the kth slice, times delta x. Now, delta x is the upper limit minus the lower limit divided by the number of slices. Okay, and that's a strategy we could use for just regular Reimann sums. And you'd be like, well, how wide is each slice if they're all equal? So that's going to be here. So because remember, whatever slice we're at, we're starting at the left on 5 plus all the slices, right, times the thickness of each slice. And that will give us the x coordinate of whatever slice we're at. The 5th slice, it'll give us the coordinate of the 5th slice. Now we got to raise this to the 4th power because that's the function we're doing. So all this right here, this is all x. And then we've got to multiply by delta x. Because remember, x equals a plus k delta x. And then we get another delta x right here. So there you go. That's the setup. This expression is the exact value of that integral. Let's try another one. 0 to 3 of sine pi x dx. If you want, pause the video and give it a try. See how far you can get. And then we'll write the rest and we'll try a few more. It's definitely involve the limit as the number of slices in goes to infinity. Summation k equals 1 to n. And then it's going to involve sine pi, but then we got to figure out what to put in for x. It's going to be the low. Well, probably should find delta x because we're going to use that for some other stuff. So delta x equals the upper limit minus the lower limit divided by the number of slices, which is n. So the x value is going to be the lower limit, 0, plus how many slices we're at, the kth slice, times the thickness of those k slices that we've had so far. And that's going to give you the correct x coordinate. And then we got to multiply by delta x, which is 3 over n. So there you go. There's the answer. Of course, we could clean it up. Limit as n goes to infinity of summation of k equals 1 to n of sine. Now, what would probably happen if you're choosing an answer like this from multiple choice, they would clean it up. They'd say 3 pi k over n, all one nice expression. So this is a little more cleaned up version of that answer. Okay. Now, that's going one way, and I feel like that's the easier way. The other thing you're going to have to do is that you're going to have to take things that look like these answers and work backwards. And so, of course, at first, it's going to feel more difficult because it's brand new. But let's see if we can figure it out. I mean, if you understand how to put them together, it's going to make more sense to help you figure out how to pull them apart. So let me give you an example of the limit of a Riemann sum. And we're going to try and figure out what the integral is. So we got to figure out, this is probably our x coordinate, which is the lower limit plus k times delta x. So that probably has a lot of good information. So we're probably going to start at 3, right? And then the delta x, so this is, that's that. The delta x says delta x is the stuff without the k equals 5 over n. And since delta x equals the top limit minus the bottom limit, which we said is 3 divided by n, then we can figure out what the top limit is. The top limit should be whatever you subtract 3 from to get 5. It's 8. Right? So from that, the function, if we consider the x to be down here, is going to be 1 over x dx. So then what's going to happen possibly is on the AP test, they might give you this, and they might give you answers with integrals, and then you'll try and pick the right one, or they might not give you answers with integrals. They might give you answers with numbers in it. You got to figure out, what does that equal as a number? Like, I don't know how to do that. Change it to an integral, and then integrate what's inside, just using regular integral rules, and subtract. And then a lot of times, especially in multiple choice, I mean, you could leave this as your final answer and free response, but on multiple choice, they'll probably use log rules to combine them together. They probably do natural log of 8/3. Okay, now here's the deal. We could try there could be other interpretations of this as far as this goes. The answer should come out the same no matter what. One way is to say that this is all part of, we could say that the 3 is part of the x, okay? So we could say that instead of 3 plus kx, it could be 0 plus k delta x. And so we could say that the 3 plus is sort of like separate, that it's just there, right? And so we could just say that this right here represents the a plus k delta x. And we could say that a equals 0. What I'm saying here is that we're starting at 0 instead, and that the function has x over 3 in it, right? Or 3 plus x, and maybe it'd be better write it so it looks more like that, 3 plus x. So we could say, well, the 3 plus is just part of the function. Like before we said, oh, the function is going to be 1 over x. Well, we could say it's 1 over 3 plus x. But then that means that here's our x. We'd have to treat the initial term as the lower limit as 0. And then our delta x is still going to be the same. By the way, here's your delta x also. But if we're starting at 0 and the upper minus lower limit is 5, then we're going to go up to 5. So this is another interpretation as an integral. Now, if you integrate this, guess what? You're going to get the same answer that we got for the other one. We should, right? Natural log of 8 minus natural log of 3 equals natural log of 8 over 3. Same answer. So just realize you can set these up different ways. So let's try a couple more of these, because these can get a little weird, but I think you'll get the hang of it. I think it's a little easier going the other way, at least at first. All right. So here's one that's been given to you, already done. I mean, if you want, you try and pause the video, see how far you can get on your own. But we're trying to write an integral that's exactly equal to this. So I would say there's definitely a natural log, right? That's definitely part of the function that is determining the curve that we're trying to find the area under. So this whole thing could be our x, a plus k delta x. And so a would equal 2. That would be our lower limit, right? And then we would have to figure, now this is minus, so that's a little weird. I mean, are we going to say that k delta x equals negative 6k over n? I mean, it's kind of an interesting idea. If delta x is negative, which it's right here too. Now, if it's negative, maybe there's a negative there, and there's an extra negative that we'd put out in front. So we'd put this extra negative out in front. And then, so there's your delta x, and it equals the upper minus the lower divided by n. So upper minus 2 equals negative 6. That means upper must be negative 4. So this one's kind of weird. We were kind of integrating backwards, and then we need an extra negative here. And then that would be natural log of x dx. So maybe that's one way. And you we can't integrate this one, by the way. You can't integrate natural log x, so you'd be done. Let's look at some other creative approaches. Let's imagine the 2 minus is just part of the function that we're trying to find, and that's going to be a little nicer. So we're going to assume that's natural log of 2 minus, and that this whole thing right here is our delta is our x, which equals our lower limit plus k delta x. Now, if there's no number there, like the 2 minus is separate, there's no number there, then that means that a must be 0. So we're going to start at 0 on the lower limit. And then k delta x is going to be 6 over n. So if our lower limit is 0, then upper minus lower to get 6 would have to be 6. And then we would just put x here. And then we do dx. And so this is another interpretation, which we can't integrate. There's even another possible interpretation where we say, you know what, let's think of this as natural log of the negative of negative 2 plus 6k over n. And then that takes care of the issue up here. This negative was messing up, or is just making it weird. So now your a value could be negative 2, and this is your k delta x. So that's your delta x. So we're going to start at negative 2, and we're going to do natural log of the negative, and this whole thing is going to be our x value. So it's going to be natural log of negative x dx, and the change between upper and lower limits is always 6 on all of these. So it just depends. Wherever you start, add 6 to it, and that should give you the same thing as this does. So anyways, several different ways of thinking of it. You can kind of change the way you approach it. So that was kind of challenging. Let's do one more on these notes, and then maybe we'll try a few on the homework assignment. Now, of all the, like I said, I don't know, you might only see like one problem on the whole AP test involving this. So I think, I think if you invest a little time in it, not too much, that you should get the hang of it. And it's actually kind of a predictable thing. It's not like a hard thing, but it's weird because we just haven't talked about it before. Now, okay, I'm not going to do this one, but just something to point out that sometimes they'll put this number out in front, which is the delta x, which doesn't involve k. So anything that doesn't have k could be in front of the summation with the k's. N is going to infinity. So delta x could be in front since it doesn't involve k. So be aware that things might not be so nicely in order the way we like to think of them, the way that kind of makes sense. They might kind of mix some things up. So you got to be sort of ready for that. So that's those notes. Now, there's a worksheet that goes with these, and you should print it out. If you haven't, pause and print it out. It's labeled worksheet 12 7B in the shared folder. And I thought maybe we could just try a couple examples together just to help you see a couple more. So it doesn't say worksheet 12 7B on it, but the title of it in the shared folder is. So we could write worksheet 12 7B on it. And it has two sides. And I think each side kind of takes a different approach. So it has some formulas written on it that we already talked about. It has this sort of idea right here that that integral can be the limit of the summation of, and this is your expression for x, and this is your expression for delta x. Okay, so this is what we've been doing, and here it says x equals a lower limit, right? Lower limit plus k delta x, and delta x dx equals the upper minus the lower limit. Now, don't memorize that because it's just like, well, how wide are all the slices going to be? We'll find the difference and divide by the number of slices. Okay. So let's see. Let's just try these first few. Go ahead, maybe try and pause the video and see if you try these first three, and then I'll go back and do them. But the best way for you to get the hang of this is to actually force yourself to start trying it. Okay, so let's see. We're trying to write an integral with this, right? Now, you should see the function. I think it's going to involve, maybe x to the fourth dx. I don't really need the parentheses. Now, this is probably our delta x right here. Some number over n is going to be your delta x. And then this is going to be your x. Now, remember, x equals the lower limit plus k delta x. And so you see the 1 over n there? That's your delta x, and there's the k. This means that a must be 0. So that's the lower limit 0. And then the difference between the upper and lower limits is 1, so that's going to be 1. And you're done. So these can be, it's going to be faster. Now, this next one, realize, hey, there's your delta x hanging out. Usually we like to think of it as over here, but that's fine. It can be right there. You should see your k delta x right there, k delta x. And if it's all being squared, then that means your x, that's your x has to be in there. That means this 1 right here has to be separate from the x. So we're going to write an integral, and I think it's going to be 1 over 1 plus x squared dx. Don't forget the dx. And by the way, we could integrate this one, right? X to the 5th over 5, 0 to 1. 1/5 minus 0/5 equals 1/5. This one right here, let's figure out. We still got to figure out the limit. So if this is our x right here, x equals a plus k delta x, then that means that a has to be 0. A cannot be 1 because that would have to be part of the x, which is inside whatever's happening here that's squared. And since the plus 1 isn't being squared, that can't be part of your x value. So it's going to be 0. The difference between the upper and lower limits is 1. So there you go. There's your integral. Now, if we were to integrate it, this is inverse tangent of x. You guys remember that one? Don't need a plus c. It's a definite integral. And then we could plug the top limit in first minus the lower limit in. And inverse tangent saying, well, what angle do you take tangent of that gives you 1? Well, that'd be when sine and cosine are equal to each other, which would be pi over 4, right? And this is also, inverse trig is going to assume principal angles. What do you take tangent of that gives you 0? Well, it's sine over cosine. So when is sine 0? 0. Okay. The next one, let's see. This right here appears to be our delta x. It's a number over n. So it's the difference between the upper and lower limits divided by n. And then this is probably going to be our function. Now, you see the 2 plus k over n, the 2 plus k over n right here? That means there's 2 x's. X equals... So we're going to have x's show up in multiple places of our function. Like, oh, that's crazy. Really? You've never seen like a polynomial with multiple terms that you're integrating that has more than just one place where x shows up? So it shouldn't be too crazy. Okay, now if we're going with each of these are x, then that's your a plus k delta x, and there's your delta x 2 over n. Now this is kind of weird because you know what? Oh, because this should have the 2 right there. So I think the 2 isn't going to be part of the delta x. I think it's like we're just going to move the 2 out front. And we could put the delta x over here, the 1 over n part, because you have to see the delta x in here and there's no 2's. So one way is to say, let's just move the 2 in front like a constant. Okay? All right? So when we write this, it's going to be 2 integral, the lower limit's 2, and then the difference in the upper and lower limits is 1, so it's going to go up to 3, and it's going to be x squared plus 3x dx. And you need to put parentheses around that expression. So there you go. So it's definitely not going to be 2 to 4, okay? Or it's not going to be 2 to 4 like that. Because otherwise you need 2's in here, which we don't have. Maybe there's another way to kind of get around that. Now, another way to think about it is to say, well, let's say that the 2 isn't really part of the x, which I don't think is great here. Like these guys, you could say, well, this is your x value. So then it could be like 2 plus x squared plus 3 times 2 plus x. Like, guess you could do it like this. And then your lower limit would be 0 and your upper limit would be 1. So this gives you the same thing, right? But the first one I think just makes more sense. And you could integrate x cubed over 3 plus 3x squared over 2, 2 to 3, 2 times 27 over 3 is 9 plus 27 over 2 minus 8 thirds plus 12 over 2. It might have been better to leave this as 27 thirds because then you get 27 thirds minus 8 thirds is 19 thirds. And then you have plus 27 halves minus 12 halves is plus 15 halves. And then we'd have to give least common denominators and stuff for that. So let's add one more example up here at the top. Let me just give you one the other way, okay, just to remind you, okay, because we've been doing a bunch of these new ones. Okay, so you're going to have to be able to do them both ways on, I think pretty much all of these are the one way, but these ones should probably feel a little easier now. So if you take a definite integral, can we rewrite it as the limit of a Riemann sum? Well, it's going to be the limit as n goes to infinity of sigma k equals 1 to n. And then what we got to figure out is like, okay, well, the function is going to be 1 over cosine of, and then this is where the x is. Now, this x is the lower term because we got to figure out where we're at on the 50th slice, for instance. It's not going to just be 50 times the thickness of all the slices before. It's the starting point plus the number of slices times the thickness of the slices. So in this case, this is your starting point 5, right? So it's going to be 5. And then k times now delta x is the top limit minus the lower limit divided by the number of slices, 2 over n. So it's going to be 2 over n. So that's what goes in here. 5 plus k times 2 over n cubed. And then you got to do times delta x, which is 2 over n. So this is your, that's the other way. Okay. All right. Try these other problems. There's problems in the front and the back. I'll try and give you guys an opportunity to ask to do some of them. I'll try and put the answers up, at least just the solutions, so you can check them. And that's it.